Hello, my name is Yue, and today I will talk about some semantics of first-order Horn clauses, and particularly the coinductive operational semantics, which is the focus of the talk, which is part of my research done during my PhD years. So I wrote a star here means this is the major topic of this seminar, and I wrote B here. The B means just background, and I will start from the first step. I will start with the syntax, and then move to operational semantics, inductive. This induct dot means induction, inductive, and this coinduct dot means coinductive. And I suppose some of you may not be familiar with the concept of coinduction. So this part of the background, inductive and coinductive denotational semantics, is also a major part of this seminar. So we'll start from the syntax and move to the inductive operational semantics, and then denotational semantics, inductive and coinductive both. And then finally, I will talk about the coinductive operational semantics. Okay, by a first-order Horn clause, I mean first order. By a first-order Horn clause, I mean a formula of this form. A is atomic formula, and this is implication, and this is the conjunction of possibly zero atomic formulas. Means the conjunction of this part implies a zero, and A is atomic formula of the form predicate followed by a list of first-order terms. P is a predicate symbol, and the first-order term is either a variable or a function symbol followed by a possibly empty list of terms. And some of you may be familiar with this syntax, so it's a brief review of that. Okay, that's the syntax of first-order Horn clauses. And next, as part of the background, I will review the operational semantics. This inductive operational semantics, which is also known as the resolution rule. The rule has this form. This is this is what we know. We know that the conjunction of the left-hand side implies the right. Sorry, the conjunction of the right-hand side implies the left-hand side, and we want to prove the conjunction of all these atomic formulas. And we know this one, and want to prove this one, and what we can prove instead is we copy this part here and replace this A by the right hand side of this rule. So it's A1 AM. And this part is copied here, but this part is expanded to this part according to this rule. This is known as the resolution rule. A very simple form. There's no unification involved. Now, so the concept of unification. The concept of unification is making two terms the same by making substitutions over variables. Right. For example, the unification of these two first-order terms is to unify them means to make them the same. So we need to make a substitution: x replaced by b, and y replaced by a, and we get the same term, which is ba. This is what is known as unification. It's the process of making two first-order terms the same term by replacing some of the variables. Okay. And the next step, we introduce the background of denotational semantics. And both the inductive and coinductive. And as an example, we consider some example programs. Consider this very simple program P1. There's 3 clauses. So the program P1 contains 3 clauses. The first one says, and the conjunction of Q and R. The conjunction of Q and R implies P, and Q is true and R is true. That's the second program, P2. This is the second program. It's the same as the first, except for the second clause. It says Q and R implies P, and P implies Q. So it's kind of interdependency. The cycle is circle here. And the third program, again, it has the clause Q and R implies P, and R is true. And we have no knowledge about Q. So we take these 3 simple programs as examples and demonstrate their denotational semantics, both in the inductive sense and in the coinductive sense. So let's concentrate on this proposition P. And according to, if we want to prove it with respect to the program P1, what we do is we take the first clause, which says if we want to prove P, we have to prove Q and R. And Q is right, and Q is true, and R is true. Therefore, P is proved. Okay, and in the second, if we want to prove P with respect to the second program, so this is P1. Again, we use the first clause, which says the truth of P depends on the truth of Q and R is true. And the truth of Q depends on the truth of P. And we can do this repetitively. The truth of P, again, depends on the truth of Q and R, etc. This is an infinite tree. And this is what happens when we want to prove P with respect to the program P2. We get this infinite tree. And if we want to prove P with respect to the third program, use the first clause, we have to prove Q and R. R is true, but Q is there's no clause saying this establish the truth of Q. Therefore, P cannot be proved with respect to program 3. And next, we compare the senses of true and false. Like for program P2, this particular proposition, it is not true in the same sense as this P is true, because it does not have a finite proof. But it is neither false in the sense of this program, because in this case there is some node that has no support. But in the proof tree of P, every node has a support. So this particular P, it is not as true as this one, and it is neither as false as that one. And there's a special sense of truth, and we call it coinductive truth. And regarding the denotational semantics, what this means. This word denotational means what can be proved. Proved from or follows. This denotational means what can be proved from or what logically follows a program P. So when we talk about denotational semantics, we mean what can be proved from this program or what logically follows from this program. And in this regard, it is often useful to regard programs as operators. And how to do this? How to regard a program as operator? We have to first define the domain and codomain of the operator. In all of this example, all of these three example programs, they contain the same set of predicate symbol or predicates or propositions, which is P, Q, and R. And we name this set as B, and we regard these programs as operators on this program PI. They are regarded as operators from the power set of B to the power set of B. This is a type of these operators. And now we see the definition of these operators. Let's say P1 first. It has three clauses. The first one, the second one, the third one. The first one can be read in this way. If Q in the some set S and R in some set S, then P is in the result of applying this program, applying this operator to the set S. And second clause says, actually the second clause can be written in this way. And there's no right-hand side. It means it says if nothing is in S, then Q is in that. In other words, it means Q is in S, Q is in P1S for all. Or S. So the premise is accuracy true, and the same is for the third clause. It says R is in P1S for S. In reading this way, it is quite obvious that this program P1 can be regarded as an operator on the power set of P, Q, and R, and it may not be that obvious for you to see. So I will try to add some more details. So let's say the power set of let's list all possible subsets of this small set. So that would be the empty set, the set that contains P, the set that contains Q, and the set that contains R, and the set that contains P, Q, PR, QR, and PQR, and we'll call this column the set S. And here we want to get the result of applying of this operator P1 to S. Let's calculate one by one what is the result. So if S is the empty set, what is P1S? And the way to do is check. First follow this first clause. If Q is an S and R is an S, then P is in P1S. Because Q and R are none of them are in the first set. Therefore, P is not in P1S. But Q and R are in there. And the result of applying P1 to the set P is Q and R. Yeah, this. And apply P1 to the set that contains Q, because R is not here. P is not in the result, but Q and R is here always. Here. If you can't follow the examples, you are please feel free to interrupt, and I will slow down. And let's see, apply the operator P1 to the set PQ.
It's probably better to slow down. I can't get why the image of empty set is PR or something.
Good. Okay. Start from the first one. Which one? Which one could you make?
The first one.
The first one. Which one? Sorry.
The one where input is empty set.
Oh,
the first one.
Okay. And if we replace this x and if we replace this s by this empty set, this rule says if Q is an empty set and R is an empty set, then P is in P1 empty set. And this is false. Q is not in, so this is false. This is false. The premise is false, and well, we cannot infer that P is in the result, because this rule says if Q is in this input and R is his input set, we can infer that P is in this input set. But because neither Q nor R is in the empty set, therefore P is not in P1S, P1 empty set. But however, the second rule says Q is always in the result of applying P1 to S for all S. Therefore, Q is in the result, and for the same reason, R is in the result. Is it understandable now?
So you are writing a point-to-point trace of P1 and not P2.
I'm writing a point-to-point listing of P1. Yes, I'm trying to list all possible input for P1 and trying to compute the output of P1. Do you have any further questions?
Okay, I by some reason thought you were talking about P2 because your point-to-point list is under the line where ifs are written. So I thought it is related to P2 and not P1.
Oh, it's just for P1. So this is
okay.
This is just for P1. So our example, make it in the environment. So we will make the list one by one, and we start with P1, and try to. What we're going to do is to first find out all possible input and calculate the corresponding output, and we will see find fixed points for this operator. So what we care about is the fixed points. Fixed point is let's say f is f equals p. Let's say f is a set. Let's say f is a set, and if I apply some program P to this set, and we get the same set as the output, I will say we'll call this set F a fixed point of this operator. So if the input is P and Q, go back to the program P1. We have to decide now let's decide if P is in the, whether or not P is in the result. And we say P is not in the result because only input has Q but do not have R, so P is not here. And then let's see if Q, again, only Q and R are here. And in the next case, P is not in the result because Q is not in input. So only QR are in the result. And in that case, if QR are in input, we have P in the output. And also QR are also in the output. And for the last case, because Q and R are in input, so P is in the output, and Q and R are always in the output. And these are all possible input and output pairs. And the most special one of them is this. And the input is the same as the output, so we have found a fixed point, and there is no other fixed points for this program P1. We have found P1 has one fixed point, and we call it the least fixed point, greatest fixed point. For the least, I will use LFP. The greatest, I will use GFP. The LFP is for the least fixed point, and the GFP is for the greatest fixed point. And the order on the fixed point is just the set inclusion relation. If one fixed point subsumes the former one is called larger. So the least one is the least fixed point is the fixed point that has the smallest number of members. In the case of program P1, we have the least fixed point equals the greatest fixed point, which equals this set, P, Q, and R. Now for the second program, P2. The first clause says if Q, R are a member of S, then P is a member of P2S. And this clause says if P is in S, then Q is in P2S. And this third one says R is in P2S. For OS. Okay, and then for this program P2, let's see its possible input and output. So for empty set P, Q, R, Q, PR, QR, and P, Q, R. If the input is empty set, the output would only contain one proposition, which is R. Because it does not have P nor Q. P is not in the result because this empty set has no Q and R, because Q and R are not in empty set, therefore Q is not in the result. And Q is not in the result because P is not in the input. And R is in the result because it's eight. And for this one, for the second, just omit the braces and just write empty set is mapped to the singleton set that contains R. And for the singleton set that contains P as input, we have the result contains Q by the second clause. But since the input clause does not have occurrences of Q and R, the P is not in the result, but R is again in the result. And we can similarly write Q. Given Q, we have R is not here, so P is not in the result, and P is not here, so Q is not in the result, and only R is in the result here. And for the same reason, R is in the result, and in this case, and P is here, so Q is in the result. But R is not here, so P is not in the result, but R is still here. And let's say the input has P and R. We have Q in the result, R in the result, but since Q is not in the input, so P is not in the output. And in the last one case, Q and R are in the input, therefore P is in the output. And since P is not in the input, therefore R is not in the Q is not in the output, and R is in. So by the way, this kind of operators are called immediate consequence operators. The operators induced by these programs are called immediate consequence operators. Means the input is a set of propositions, and the output is just the immediate consequence of of the input. Let's say if the input contains all of the three, and the output shall contain also all of the three. For the immediate consequence of QR is P, and QR are in the input, therefore P is in the output. And the immediate consequence of P is Q, and P is in the input, so Q is in the output. And R is always here. And if we examine the input-output pairs of the program P2, we find there are two fixed points. This is a fixed point, and this is a fixed point. And all other input-output pairs are not fixed points. And this fixed point is a singleton set contains R, and that fixed point is a set contains all P, Q, and R. And this one consumes that one. So this is called this R is a singleton set. R is the least fixed point, and this PQR is the greatest fixed point. I write it. So for program P2, the least fixed point equals the singleton set R, and the greatest fixed point equals the set P, U, and R. And compare this P1 and P2, we would say that both of them have this have the same greatest fixed point, but the least fixed point is not the same. And for P2, the least fixed point is smaller. It just contains R. But for P1, the least fixed point contains all of them. And why? Because the least fixed point represents all the propositions that have a finite proof. But so in the case of program P1, all these three propositions have a finite proof tree. But for the program P2, only this R has a finite proof tree, and the rest, P and Q, they do not have finite proof trees, but they have infinite proof trees. Therefore, they are in the greatest fixed point, but not in the least fixed point. And similarly, if we follow a similar procedure of computation, we will have the least fixed point equals the greatest fixed point equals R. For the third program, because for this third program, it is only this proposition R that has a proof consists of a possibly infinite proof tree. But for P and Q, there's neither a finite proof tree nor an infinite proof tree. And we relate this least fixed point to the inductive semantics and relate this greatest fixed point to the coinductive semantics. So just a matter of definition. The coinductive denotational semantics of a program is the greatest fixed point of the immediate consequence operator that corresponds to this program. And the least fixed, the inductive denotational semantics is the least fixed point of the immediate consequence operator that is induced by this program. Okay. So let's come back to our outline. We are going to introduce denotational and operational, inductive, and coinductive. We have introduced denotational, inductives, and coinductive. This is the least fixed point, and this is the greatest fixed point. And operational, this is the resolution rule. And this is our remaining part. Okay, there's this, how they're related. So the resolution rule with respect to the least fixed point. There are two concerns. One is called soundness. The other is called completeness. And we say that the resolution rule is sound and complete with respect to the least fixed point. And by saying this, we mean that soundness is everything that can be proved using the resolution rule is also in the least fixed point. By that we mean soundness. And for completeness, we mean everything that is in the least fixed point can be proved using the resolution rule. The resolution is sound and complete with respect to the least fixed point. And now the task is to find something similar, some operational semantics that is possibly possess these opportunities. Possibly possess these properties with respect to the greatest fixed point. We want some procedure or some rules, so that every proposition proved using these rules are also in the greatest fixed point. So this one is the first thing that we want to guarantee. Soundness is the most important. If it can prove something wrong, the rule is not useful. And the completeness, the experience shows this is challenging to achieve. So next we'll focus on this part. This is the major part of the talk. What we're going to do is find operational semantics that is sound with respect to the greatest fixed point. And let's say the first program, let's say the second program, P2. Here. And operational semantics has to be finite. We are not going to accept any infinite proof. Q, E, Q, R, etc. So this kind of infinite proof is not accepted. We're trying to follow a finite procedure and try to find a finite procedure to establish the truth that P is in the greatest fixed point of this program. And the way is the solution is like this. So this is existing work. We add a coinductive hypothesis. When we do inductive proofs, we have inductive hypothesis, and when we do coinductive proofs, we have coinductive hypothesis. And this coinductive hypothesis is chosen. I take P as a coinductive hypothesis, and we say that if we want to prove P, we can use any of these clauses, but with the rule that this coinductive hypothesis cannot be used as the very first step. We must use one of the clauses from the program, and after that, we are free to use coinductive hypothesis. So let's build the proof tree for P. By the first clause, we have to prove Q and R is true. And then to prove Q, we have to prove P again. And at this moment, we can use the coinductive hypothesis. And this amounts to establish a link back to it. So another way to look at coinductive hypothesis is to try to unify P with one of its direct ancestors. This P and that P, they are kind of direct ancestors. And in this way, the proof tree becomes a directed graph. And we find a cycle here. That means taking this piece, we can reconstruct the entire proof tree because we found a cycle. And what follows from this cycle, we know that what follows here is just a repetition of this part. But this method is sound. Is everything that can be proved using this method is guaranteed to be in the greatest fixed point. Because okay, let's say some important theorem called Tarski fixed point theorem. Some notions of prefixed point. The fixed points, there are more finer definitions, or finer distinguishes, and they're prefixed points. By that I mean P as pre. Apply the operator to that subset equals as pre. So if the result of applying operator to the set is subset or equal to the set, we call a prefix point. And it's also a postfix point. And that is as post. Subset equal to the results of applying the set operator to the set. We have at the spotlight we have this subset equal relation. And we have a set and the result of applying operator to this set. If it is this kind of print, and the operator is on the right hand side of this symbol, this set inclusion symbol, we call it a post fixed point. And if the operator is on the left hand side, we call it a prefixed point. In this case, S is called a prefixed point of this operator P. And it follows that if a set is both a prefixed point and a postfixed point, then it is a fixed point. If a set S is both a prefix point and a postfixed point, then it is a prefix point. It's a very basic set theoretic result, saying that if A is a subset of B and B is a subset of A, then the two sets are equal. Okay, these are some definitions necessary to understand the theorem. Tarski's theorem says the least fixed point equals the intersection of all prefixed points. And the greatest fixed point equals the union of all post-fixed points. And this gives a proof method of showing something is in the greatest fixed point. If we want to show some element is in the greatest fixed point, it amounts to construct a post-fixed point and that contains this element. For example, why this method is sound. It is sound. It means to say this proposition is in the greatest fixed point. And to prove that it is in the greatest fixed point, we have to find a post-fixed point that contains this proposition. And this post-fixed point is actually all the propositions in this tree. Post-fixed point. What is a post-fixed point? Post-fixed means if you apply operator to this set, you get a set that is larger than or equal to the original set. If this original set contains PQR, and apply the operator to it also contains PQR, and actually this satisfies the subset equal relation. Therefore, the set containing all the nodes is a post-fixed point, and this P is in this post-fixed point. Therefore, it is in the greatest fixed point. Is this how is it? Is this still understandable? Oh. But this method has some limitations. For example, if we consider let's say, in a more intuitive way, what is in the greatest fixed point? P, QR, etc. And in this infinite proof tree, although it is infinite, but we know that using these rules, every node in this tray is well supported. It means for every node in this tray, we can pick a clause from this program to continue the growth of this tree. If everything is well supported, that means apply the immediate consequence operator. This node will be in the result, and because this P is supported, this Q is supported by this one. If we apply the immediate consequence operator to this set, it will also be in the result. Therefore, having an infinite proof, tree, it means the root of the tree must be in a post-fixed point. It means if P is in S, then it's guaranteed to be in the result of applying this operator. So to show some proposition is in the post-fixed point. It amounts to build an infinite proof tree for it. Yes, at this moment, is anything unclear? I pause for a while to answer some. If you have any questions, then please ask. And if there's no questions, I would continue limitations of this approach. What's the limitation of this approach? Consider a program. Px is implied by P Sx. Consider this program. Now, if we want to prove PA, and using this rule, we have the next go is PSA, and the next go is PSSA, etc. If we unify, there's no ancestor. We cannot unify any of the nodes in this tree with any of its ancestors. So the existing work is called simple loop detection. Using this plus, it says there's no concrete coinductive hypothesis. There's no concrete coinductive hypothesis. We cannot find any coinductive hypothesis from this set of atoms. There's no backward link can be built. And the solution is we have to make the coinductive hypothesis more general. In our case, the coinductive hypothesis should be for all x, Tx. And we follow the same rule. We start from PA and use the program clause to determine the subgoal, which is PSA. And from this step onwards, we can either use this program clause or use this coinductive hypothesis. And this time, PSA unifies with this clause, and we have the proof is done. Proof is done. We'll get a substitution. X for SA. What we've done is previously, if we want to prove PA, we have to repeatedly use this clause, and we're building a finite proof tree. Now what we did is we first use this clause to get to the subgoal, and we try to unify this subgoal with the coinductive hypothesis. And it unifies, and it is done. And how we determine this coinductive hypothesis? It's a matter of, you have to find it, but there's no mechanical way for us to find a coinductive hypothesis. And it's just like when we do inductive proofs. There's no mechanical way for us to find the inductive hypothesis. We have to use some creativity to find. So the same for the coinductive hypothesis. We have to use some creativity to find this coinductive hypothesis. And why this matter works? You see, we focus on this part. Small substitution S. And we can compose this substitution with itself. Etc. It can be And we use this substitution to systematically instantiate this part. And if we apply this kind of operation to the terms of this tree, we get PSA. This is PSSA. So we try to kind of instantiate this template with using one of these composed substitutions. So we get this. And if we use this second one, we have PSSA and PSSA. Well, we always start from this segment of the proof tree, and we use this sequence of substitutions to instantiate this template. Using this composition, we instantiate the template into this piece, and using this composition, we instantiate the template into that piece. And then we can continue this process, and this time with the using this one, and it becomes this segment, and this can be done infinitely, and we get infinite collections of instantiated segments, and these segments can be assembled because you see this part and this part, they are the same, and this part and this node, they are the same, and this node and this node, they are the same. That means if we go from here and go from here and to here and to here, this kind of direction. By collecting these segments, we cover the original infinite proof tree. And in more general cases, and the substitutions may be richer. It may have multiple different constructors, and in a general case, we can arbitrarily compose these constructors. Etc. And we use these composed substitutions to instantiate some finite segment, and we get infinite family of segments. All of these pieces assembled together, we can use them to recover the infinite proof tree. Now it's time to make a summary. Simply speaking, the problem is to capture the pattern in some. We're familiar with the kind of problems like if I write a sequence of numbers, 1, 2, 3, 1, 2, 3, and ask you to keep on writing, and you probably guess what follows is again 1, 2, 3, etc. And this corresponds to the proof tree of the form like P, Q, R, Q, P, Q, R, etc. There is just one part, and you just copy and paste. You get the infinite pattern. And there's also another kind of pattern, which is, say, 1, 2, 3, 4, 5, 6. And if I ask you to keep on writing, it's very likely you will write 7, 8, 9, 10. And this corresponds to the pattern of scaling by constant factor. The scaling by constant factors corresponds to the pattern from PA, ESA, ESSA. The proof tree, in the first case, the proof tree has a uniform or periodical shape. You can this way, or it's changing in that way. And because the pattern is periodical, we can always find a part and copy and paste that part to recover the infinite thing. And in this case, the proof tree is scaled by a constant factor. That means we can take one segment and instantiate to get larger and larger pieces, and we assemble these pieces to get an infinite tree. And it is this what I did during the PhD time is I made a step from this to this. So finding patterns in the infinite proof trees, and the previous work was finding a pattern in the periodical infinite trees of periodical shape. And what I did was just finding a patterns in an infinite tree which has the shape of scaling by a constant factor. And there are some open problems. There are also proof trees whose shape is scaling, but it's not according to a constant factor. It may scaling by a power factor, or it may scales by some oscillation factor, like that kind of shape. And this is the open problems not yet studied. So I'm going to finish this seminar by making a summary of what I said. I start with some syntax of first order Horn clauses, and for the semantics, I said there are four. The semantics has two dimensions. One is inductive or coinductive. The other dimension is operational or denotational. And I reviewed the inductive and coinductive denotational semantics in terms of fixed points of operators, and reviewed the operational semantics, inductive operational semantics in terms of the resolution rules. And then I discussed the coinductive operational semantics. And this one, the existing work, which says a goal succeeds if it unifies with a previous goal. And this kind of work can deal with infinite trees that has a periodical pattern. But my work during the PhD time allows a more general form of coinductive hypothesis. and it can solve problems. It can capture the structure of infinite trees that scales by a constant factor. This step I made, and these are open problems where the trees are scaling not by a constant factor. Okay, that's the seminar. Syntax and semantics, particularly coinductive operational semantics of first-order Horn clauses. Thank you. And are there any questions? Thanks. I've finished.
Yeah, I understand. Does anybody have any questions?
Oh.
No. Well, then I have first. I wonder if there is such thing as non-periodic proofs, non-periodic proof trees. I mean.
Sorry. Could you repeat the question?
Yeah, the question is, you mentioned various forms of periodic trees, proof trees, and are there non-periodic proof trees? Do they exist in nature?
Periodic things like this kind of tree is periodic.
Yes. I'm asking about non-periodic.
And this is non-periodic.
Yeah, but it's periodic up to scaling factor. Can there be completely non-periodic trees?
This, for example, a logic or the relational program that computes the Fibonacci sequences. That is not periodic, and that is not scaling by a constant factor. It's scaling by some other factors.
Yes, but it's still scaling up to exponential, I presume. But can there be non-periodic trees? The trees with no periodic structure up to no scaling factor, etc., etc.
Possibly, I believe there exist. I never tried it, but I imagine if I write some logic program, relational program that computes some special natural numbers, like computes this number or computes this number, perhaps we'll get a non-periodic proof tree. But it's just some impression, never verified.
Okay.
So I'm not. I hope so, and I believe so, but not know for sure.
Yeah, and actually, I had another question, but you already answered it. I was wondering if the incompleteness is just a conjecture or a proven fact, but it's obviously that is a proven fact. So it's obviously not non-complete, since you mentioned explicitly the cases which you don't handle. Okay, so any other questions? Meanwhile, no.
Okay, let me try.
Okay.
So you described for us coinductive semantics as an opposite of inductive semantics. I have probably a very weird understanding of coinduction is. Why coinductive is called coinductive in this case?
Why is called coinductive? Because it's the very quick answer is there's no better way to call this phenomenon. So we have induction, and it's a dual of induction. So we just simply add the prefix co to the name of coinduction. There should be some better names for it.
Yeah, I would add it just comes from the more general fact that dealing with the least fixed point is called inductive definitions and inductive approach. Dealing with greater fixed point is called coinductive definitions and coinductive proofs, etc., etc. So it's as you said, it's just a dual term. And by the way, in some terminology we don't use in some terminology there are no such notions as greatest and least fixed point. It's called fixed point and co-fixed point. So it's just a matter of duality. And okay, I have another question. And in both semantics, you only deal with the finite terms, right? The finite terms and finite atomic formulas. They can be another source for coinductivity by means, because the terms still are defined in an inductive manner, right? But you can consider logic with rational trees when the terms are defined coinductively. Are there some relations between these two? Because you can potentially have four logics, right? Four clauses with the inductive or coinductive terms, and both can be considered in both inductive coinductive semantics. Do you have any? Do you know about any approaches of dealing with logics with coinductive terms?
Actually, these two methods, both of them are in a full form can deal some sort of coinductive or infinite terms, and particularly, for example, this one can work with infinite terms of a periodical structure, and this one can work with infinite terms of a linearly scaling structure. For example, in this case, in the program that defines natural numbers. And if x is a natural number, then the successor of x is also a natural number. And if we remove this, 0 is a natural number. If we now remove this base case, and try to pose the query, what is a natural number, and next goal will give x1, and unify x with sx1. And now we draw a backlink towards this, and x1 is now identified with x. So this substitution becomes a circular substitution sx. X is connected to sx, a circular substitution, and this substitution is regarded as encoding the infinite term, infinite tree, is s, etc. And if we will use this first method, we're using some unification algorithm, and the equation of a set of equations, and these equations are allowed to have some circular paths, and the terms so defined are cyclic terms. But this first method, in its full form, can work with both finite terms and infinite terms that are cyclic. But for the second method, we have shown it is possible to work with some non-cyclic terms. For example, the infinite streams, streams of zeros. We have cons 0 and cons 0, etc. So just this tree itself is not a. No, sorry, this is not this one. It's not stream of 0, but streams of increasing numbers. This second approach can work with streams of like that. This is 1, 2, 3. So this kind of streams, and in the tree form, this cons 1, cons 2, cons 3, etc. And this is not a cyclic term because it cannot be built from a set of equations. It can only be defined in some other ways. So yes, as long as we can encode this in finite terms, and it is possible to find a way to come up with a proof, come up with some coinductive rules to prove statements about this in finite terms.
Okay, I see. Thank you. Any other questions? You mentioned that in order for your method to work, you need to guess the coinductive hypothesis, right?
Yes.
And you say it explicitly that there are no, that you devise no method of automation. Did you think about these methods of automation since you defended your PhD? Do you see any opportunities to find more automatic methods for finding coinductive hypothesis?
There are some. There is no kind of some heuristics, so-called heuristics, means not guaranteed to work, but it's possible it may work. And some previous work of the same group of my PhD group, they try to find simple heuristics to find the coinductive hypothesis. But heuristics is not ideal.
I see. And this problem somehow resembles me the problem which we face in meta computations and superpopulation, where we try to make a driving process refined by making generalization. So maybe we will need we'll have some time discussing this issue, because it resembles me as some technique from supercompilation, when you take two nodes and try to find a generalizer for them, and the generalizer may come up as a candidate for being a coinductive hypothesis. Maybe this would improve existing state of the art by using some technique from a different area. Other questions? I don't have any more. So if nobody asks anything, we will stop.
Okay.
Nope. Thank you very much for your talk. The very hard one, the first one of this year. It was interesting to see what you were doing and to recollect some things. Okay, so thank you very much.
You're welcome, and thank you for listening.
Goodbye. Goodbye to everyone.